The discriminant can be a really useful piece of information when it comes to intersections of lines and curves. So that is what we're focusing on. Just how much of a good friend that discriminant really is. So we're going to start just by looking at this idea of intersections between lines and curves, and then we're going to take that into working with the discriminant. So if we start off with considering just a few curves, for example. So we'll give ourselves some axes to work off. Some beautiful straight lines with arrows, same like you guys would have when you are drawing them, because axes you always draw with a ruler. Okay, so we can consider a quadratic. We could consider a cubic. And let's consider something weird and wonderful as well. So a 1 over x, but translated, so moved up a bit. Okay, so each of these is y against x. And each of these represents one of our curves. Now, if we were to take other lines, okay, let's say we have a straight line that goes like this. We can see that there's 2 intersections on that curve. If we put a similar straight line through here, we get 3 different intersections. And a similar line on this one, we've got 2 intersections. So in each case, this pink line has given us different intersections. So we've got 1, 2 discrete intersections, we've got 1, 2, 3 discrete intersections, and we've got 1, 2 discrete intersections. What if our line was a bit different? What if our line went like this? There we've got no intersections. No intersections. No intersections at all. So there's a different scenario. A scenario where you've got no intersections between the curve and the line. You could also have a slightly different option. Let's go for orange. We could have a line that passes just like that. We have a tangent relationship, we have a repeated intersection. Could get more interesting on our cubic one, because we could be a tangent and another intersection. And can we get a tangent on our last one? We can indeed, because there is no limit to the angle at which we can draw these straight lines. So there's a tangent on the other one, but only tangent on one. So we've got 3 distinct scenarios. We could have that all the intersections are distinct. Okay, each time the line crosses the curve, it is a different place. We could have all like this on the quadratic, or we could have some, like here on the cubic. So all or some intersections are shared. And as we said when we talked about it, this is our tangent situation, because when you have a repeated root, you have a tangent. And then our last one, possible scenario, was no intersections. So our line never hits our curve. Now the thing is that we could just solve simultaneously and see what we get in as an answer, but sometimes we're rather going to use information about the relationship that we have in order to work with other things. Okay, so if we have an unknown, we could actually use a discriminant to get to start calculating unknowns. But remember that discriminant is only going to work when you have a quadratic situation. So if you're starting out with quadratic in a straight line, you go to quadratic. In some cases, like your 1 over x, when you multiply by that x, you can end up with a quadratic. So you could also be dealing with a quadratic situation. With your cubic, you are very unlikely to be able to get an intersection between a line and a cubic to ever get to a quadratic equation because you have that x cubed in the way. So generally when we're working with cubics, we are working with a visual understanding. So the sketch of your cubic and the sketch of your line, and then seeing what happens if my line moves, what can my different intersections be. If we took this green line here on our cubic, for example, and we slid it up, at what point would we start to get intersections with the curve? And that's how we would deal with those. When we have that quadratic thing going on, then life is a whole lot simpler because then we can start to use our discriminant. So for example, we would be looking at something like y equals x squared plus 3x minus 5, and the line y equals kx plus 1. And then they'd ask us, for what values of k does this line intersect the curve? So, well, intersections means simultaneous equations, and off we go. But the thing is that when you do simultaneous equations, 2 equations solves for 2 variables. We can't solve for 3 variables. So y, x, and k, we have 3 variables. And that's why we need to now start thinking a little bit outside the box, okay? So if we have this intersection, then how will we solve for values of k? Not for y and x, because they didn't ask us where are the intersections for this line and this curve. They asked us for what values of k does the line intersect the curve. And it's quite a big difference in that. So how do we go about approaching something like this? Okay, well, we know that ultimately we would want the line and the quadratic to have intersections. So the first thing we would set out to do would be simultaneous equations, because intersections are based on simultaneous equations. So our first step will be simultaneous equations to combine the curve and line. And what you end up with as it is an equation that represents the solutions of those intersections. So it's an equation that represents the intersections. So once we've represented our intersections, we would need to get a quadratic equals to 0, because that's the only time we can do anything fun with a quadratic. And then once we have quadratic equals 0, we can apply our discriminant. So just to give you a little bit of an idea of what this would actually look like. Okay, so let's say we have a quadratic and we have a line. Okay, so obviously we can see here we have 2 distinct intersections. So what we would do is we would take our quadratic and our line and we would put them together. We're getting an equation now that represents those 2 intersections. And what is really cool is when we do that, we effectively create a new quadratic that crosses the x-axis. Now this situation here is exactly the same situation that we were dealing with when we worked with the discriminant. And you can see we had 2 intersections here, 2 intersections with the axis. So of course, if we were dealing with a slightly different situation, if we were dealing with a situation like this, our quadratic doesn't touch our line, then when we rearrange, our quadratic won't touch our x-axis. There's no intersections. There's no roots to that equation of the intersections. Okay, if we had the other situation, No roots, 2 roots. What if we had tangent to our quadratic? Then when we rearrange, that x-axis is going to be the tangent to our quadratic that's representing the intersections. And it's wonderful because it doesn't matter where you start, with what line, with what quadratic. When you do that algebra to combine them into one equation, you end up with one of these 3 situations. So we don't have to worry about drawing that new quadratic that we've created, because what we're going to do is we're going to use it. We're going to work with the discriminant. So you're going to apply the discriminant and solve for k, or a or b, or whatever it is that's an unknown in your line or your curve. But once you've got that relationship, we missed a number here. Once you've rearranged that relationship of your line and your curve to get to a quadratic that relates to the axis, then you are sorted to apply that discriminant, and then you can get your answers. Are we happy? I've got a few examples to work through to show you how this actually looks like in real life. Are we good to continue on with those? Okay, cool. Let us go. So, let us start with something nice and straightforward. We have y equals x plus k. Gradient of 1, intercept, unknown. And we have y equals x squared minus 3x minus 8. Quadratic, intercepting at minus 8. And we are told, find values of k for which the line is a tangent to the curve. So there's a few things in here. We have y, x, and k. 3 variables, but only 2 equations. So we have an issue. Can't solve as we were just sort of straightforward. But they also ask us for k. Not for x, not for y. They don't care about x and y. They care about k. For which the line is a tangent to the curve. There is your trigger phrase. The trigger is your discriminant. So we start out by understanding the intersections. So we're going to create that equation for the intersection. So we know then x plus k equals x squared minus 3x minus 8. Straightforward substitution. Quadratic must equal 0 before we can have fun. 0 equals x squared minus 4x minus 8 minus k. So things are a little bit more interesting than when we did the discriminant before, because we can often have now extra letters in there. So if we think nicely, what are our a, b, and c for our discriminant? Well, we have a 1 hiding, of course, by our x squared. We have a minus 4 for our b, and we have a minus 8 minus k for our c. So we must be sure that we take that whole a, the whole b, and the whole c, and the whole thing includes its signs. So we know that for tangent, we must have b squared minus 4ac equals 0. The root must be repeated. The intersection must be repeated. So, for value of k, we would need then b squared minus 4 squared minus 4ac equals 0. And we set up our discriminant properly the first time we use it. Okay, always with what's happening on the right-hand side. So minus 4 squared is 16. Minus 4 times minus 8 plus 32 minus 4 times minus k plus 4k equals 0. So 48 plus 4k equals 0. 4k equals minus 48. And k equals minus 12. So if you have the line y equals x minus 12, it's going to form a perfect tangent to the quadratic y equals x squared minus 3x minus 8. So we didn't solve for x, we didn't solve for y, we just solved for that value of k, using the information in the question to tell us which version of the discriminant to use. So another one. Y equals 2x minus 2, y equals x squared minus k. Doesn't matter if our unknown is in our line or in our curve, it all works exactly the same way. In this case, we are told to find the values of k for no intersections between the line and the curve. Now, as soon as we see no intersections, we are triggering b squared minus 4ac is less than 0. So we start in exactly the same way. We have a 2x minus 2 equals x squared minus k. We're setting up that concept, that idea of that intersection. Quadratic must equal 0, x squared minus 2x plus 2 minus k. So in this case, a is 1, b is minus 2, c is 2 minus k. So for values of k, to justify why we're changing from this equation to do something completely different all of a sudden, b squared minus 2 squared minus 4ac. And in this case, b squared minus 4ac, no intersections, less than 0. And then we do exactly the same thing. Minus 2 all squared is 4, minus 4 times 2 gives us minus 8, minus 4 times minus k plus 4k less than 0. So 4 minus 8 minus 4 plus 4k less than 0. 4k less than 4, k is less than 1. And you see here we ended up with a zone for an answer, values of k. If k is anything less than 1, then this curve and line are not going to intersect. So if we have x squared minus 3 for our curve, it's not going to touch our line. Okay, and that's how we then work through everything over time. Always the same thing. Intersect, and then get your quadratic equals 0, and then find your values of k. We've got one more, which we're going to sprint through to fit in because it's slightly different again. So we have y equals k plus 1 over x, and y equals x plus 3 over x minus 1. Values of k for 2 distinct intersections. Obviously, they'd put a few more words than this in the full question. Okay, 2 distinct intersections is your trigger phrase, b squared minus 4ac greater than 0. But things are a little bit more interesting here because we have not that straightforward line and quadratic, but we're going to trust them because they've given us a setup for a discriminant, in which case they should have a good idea. So k plus 1 over x equals x plus 3 over x minus 1. And we can see straight away as soon as we go for this that we can trust them. We are going to get that quadratic to work with. Because when we clear this over x, we multiply through by x to clear those fractions, kx plus 1 equals x squared plus 3 minus x. And there we see we are set up beautifully for a quadratic. So 0 equals x squared minus x minus kx. And then the 3 minus 1 gives us a plus 2. So remember we need one coefficient of x. So 0 equals x squared plus, we always have ax squared plus bx plus c. So plus minus, not minus x, minus 1 minus k times the x. And if you multiplied that x in, you would have, that's your factorizing out to get the coefficient just of x plus 2. So now we can go for values of k. And we're starting out exactly the same like we did the other two examples. B squared minus 1 minus k all squared minus 4ac. Two distinct intersections greater than 0. Minus 1 minus k all squared. So minus 1 times minus 1 gives us 1. Minus 1 times minus k, k, so plus 2k, and then plus k squared. Minus 2 times 4 is 8, still greater than 0. So if we rearrange this, make it look a little bit more sensible, k squared plus 2k minus 7 greater than 0. And now your brain should be firing on all sorts of different bells. Because here we have k squared greater than 0. We have a quadratic inequality. So we can't just solve this inequality like we did the previous one. That was a linear inequality. We could just go down. Now we've got to get our critical values. So for critical values, we know that k squared plus 2k minus 7 equals 0. And we sit and we look at that and we say, factors of 7 that subtract to give 2? I don't think so. So we can't actually factorize this one. But if we can't factorize it, we've still got our formula. So we know that k equals minus b plus or minus square root b squared minus 4ac. So 174, 4 times 7 gives us 28. So it is a plus 28 all over 2a all over 2. So you're not writing out that full formula. The formula is in your formula sheet anyway, and you should know it by now. What's important is using it. So we can plug into our calculator. Minus 2 plus the square root of 32 over 2. And minus 2 minus the square root of 32 over 2. And that gives us k equals minus 1 plus 2 root 2. And k equals minus 1 minus 2 root 2. Two answers for our quadratic. After we've got our critical values, we are going to mini sketch. Minus 1 minus 2 root 2 is smaller than minus 1 plus 2 root 2. And we are looking for the relationship where quadratic is bigger than 0. So we're looking for these two zones. For our values of k, for the final answer for our question, therefore, is k is less than minus 1 minus 2 root 2, or k is greater than minus 1 plus 2 root 2. Two zones for that final answer for k. And as it's pure maths, we leave it in the exact format. We leave those surds in unless we're told otherwise. We like to be nice and accurate with those final answers.